All right, this will be a brief tutorial on heat engines and work in heat and efficiency of those engines, including the Carnot efficiency. If you look, what we have, we're going to look at the efficiency of a engine. In that, we've got a high temperature reservoir where we're going to draw QH, and a lower temperature reservoir where we're going to deposit QL. It'll be a TL. You'll get a larger amount of heat coming out of the high temperature reservoir. Some of that will be converted to work. The rest will go into the lower temperature reservoir as heat. But the heat in the high temperature reservoir equals the heat in the low temperature reservoir plus whatever work. So this plus this should equal this. Otherwise, you're violating the laws of thermodynamics. And so to look at the efficiency of this particular engine, we're taking 1200 joules from the high temperature reservoir, so this is 1200 joules, and we're doing 400 joules of work, so this is 400 joules. So the efficiency, so for part A, the efficiency is equal to the work divided by the heat from the high temperature reservoir, or 400 joules divided by 1200 joules. So you just divide that out, 4 divided by 12, or 400 divided by 1200. Essentially, it's a third, so 0.33, or you could say it's a 33% efficient engine, which as far as engines go is actually pretty efficient. Your standard automobile engine struggles to get to 30. Now, how much heat's released into the cycle? So if this is true, then the heat released to the low temperature reservoir, essentially it's going to be the heat in the high temperature reservoir minus the amount of work you did. So 1200 joules minus 400 joules equals 800 joules of heat released to the lower temperature reservoir. Now, what about the Carnot efficiency? Carnot's engine is an ideal heat engine that lines everything up in the perfect way. It assumes a reversible cycle, and which is not realistic, but it gives you the maximum possible efficiency of the engine. An engine that would exceed that efficiency tends to violate the second law of thermodynamics. You can't convert heat completely to work 100%, and you can't have the heat in the low temperature reservoir plus the work to add up more than the heat withdrawn from the high temperature reservoir. That violates the first law of thermodynamics. But you can't get a bigger efficiency, even if they do add up to be more than the Carnot efficiency, or it violates the second law of thermodynamics. So what we want to do is we've got two temperatures. Steam turbines do the best at approaching the Carnot efficiency because everything's in the gas phase, and you can get a quite large temperature separation. When you get a large temperature separation, you can get a higher efficiency, which works better in the gas phase than when you're dealing with liquid fuel like gasoline. So steam turbines are about as close as you're going to get, and those are popular in power generation. But for the Carnot formula to work, we need to convert those temperatures to Kelvin. So we'll call this TH, we'll call that TL. So TH equals 400 degrees Celsius plus 273, which will be 673 Kelvin. The temperature of the cooler reservoir is 120 degrees Celsius, and usually you want that temperature to be near 100 because when you go back to cycle it through again, you want to be able to condense that water back out if you're dealing with steam. So 120 plus 273 will be 393 Kelvin. So then now we're ready for the Carnot efficiency. So the Carnot efficiency is going to be the higher temperature minus the lower temperature divided by the higher temperature again, which is why big separations equal high efficiency. The bigger the difference between these two temperatures, the better your efficiency is going to be. So 673 Kelvin minus 393 Kelvin divided by 673 Kelvin. So we're going to run that math through our calculator. And that gives us about 42.42 or 42% if you prefer, which that's a lot more efficient than the other engine that we just did. So now for part B, if the turbine takes in 500 kilojoules of heat in each cycle, how much work could you do? Well, we know the efficiency, right? So the efficiency is equal to the work divided by the heat from the high temperature reservoir. What we don't know is the work. So the work is equal to the efficiency times the heat from the high temperature reservoir, or 0.42 times the 500 kilojoules, or you get 208 kilojoules of work per cycle. And well, I rounded this off. I held the whole number of my calculator. So if your number is slightly different, that's why. Now, a heat pump is designed to pump heat in the opposite direction. That is, if you've got your high temperature reservoir up here, you got your lower temperature reservoir here. By my supplying the work, instead of getting work out of the system, I supply the work. I can transfer heat from the cooler reservoir and then dump that heat into the higher temperature reservoir. That's how you heat your house, for example, in the winter. You're pumping heat from the lower temperature reservoir to make your house warmer, but you have to supply work through the heat pump. That's also how your refrigerator works. You have an electric motor doing work, and that allows us to pump heat out of the refrigerator and outside of the refrigerator into the room via the coils on the back. That being said, if we do 200 joules of work to remove 300 joules of heat, how much heat would be delivered to the higher temperature reservoir? Well, QH is equal to QL plus the work you did. So to remove 300 joules of heat from the lower temperature reservoir, and I do that much work, you're just going to have to add them together. So I would add 500 joules of heat to the higher temperature reservoir, or I would impart that amount to the inside. That's why a heat pump works, is I do a little bit of work, I pull a little heat, but I dump more heat into here than I removed from outside, which is why that works. As long as it's not too cold outside, that works actually rather well. Right, this has been a brief tutorial on the calculations involving heat engines and efficiency and heat pumps.